All right, so here we want to just look more at the idea of making and working with scale diagrams. And what I have here is an example of a scale diagram. You know, for example, I can see the width of this image is 24 meters, and it's obviously not actually 24 meters in front of us. So this is a scale down. This is a reduction of some actual image that is, or object that is 25 meters wide and 12 meters tall and so on. So what I want to do first for this diagram is determine the lengths of all the missing sides, A, B, C, D, and E. You can see them labeled. And so first, if I zoom in this, just to remind you that these little ticks or hash marks we see here, they show that which sides are the same length. So I can see right now that sides A, B, C are all the same length because they all have one of these little hash marks, and side D and this other side over here are the same length because they have this two of these hash marks. So that's how we kind of denote multiple sides of the same length without just cluttering it up with a whole bunch of different numbers. And so from this, we have enough information to figure out all the missing sides. Oh, and E, figure out side E right here. Okay, so first, if I want to find the length of these sides, I think the most obvious one is that if this measurement from here to here is 9 meters, which means this must be 9 meters, which means D must be 9 meters. And so right here, I'll just kind of write that D is 9 meters. All right, well, if D is 9 meters, that means this distance from here to here is 9. And we know all the way across is 24. Well, now I can figure out what side B is, because these two sides together are 18 meters. And yet all the way across is 24 meters. So side B must be the difference between 18 and 24. Must be 24 take away 18. And so side B must be 6 meters in length. And so if side B is 6 meters, so is A and C. So A, B, and C are all 6 meters in length. All right, so all that's left is side E. Now if I look at side E, you may assume it has to be half of 12, because 12 is the distance all the way from the top to the bottom. Unfortunately, that's not a good assumption to make unless we have a reason to know whether or not it's half. All I know is that it's 12 meters all the way from the bottom to the top. But how do I know this distance for E really is exactly half that? I don't, at least immediately. However, I don't have to guess because remember, I figured out the lengths of A and C. So this distance from here to here is 6 meters. Whether you think of that as the distance of C or A, it's the same thing. And I know all the way from the top to the bottom is 12 meters. So now I know with certainty that the length of E must also be 6 meters because it's the only way you can all add up to 12. All right, so keep in mind, there's nothing wrong with literally labeling every single side on a diagram, but after a while it tends to get quite messy, or there's just so many values. And so we don't usually have to literally label every single one to actually be able to figure out what all the different measurements are. But we should also never have to assume. Like I said, it shouldn't have to assume or guess that something is half of some other length. There should always be a way to make it 100% clear. All right, so now I want to actually make a scale diagram. So if I look at this image up here, I can see everything's in meters, and I want to make a scale diagram of it on this grid here, in which every one square edge on the grid is the same as 150 centimeters on the diagram up here. And so with that said, let me write down this scale. One square edge to 150 centimeters. And remember, by convention, a scale for any scale diagram, the first value is always the distance on the diagram. That's what we're about to make. And this is meant to be the distance in real life. Okay. Now, one thing I would say, because I'm trying to relate it back to this image up here, is that all my measurements up here are in meters. And so I can either change all my measurements up here into meters, or I can change this 150 centimeters into meters. I said that wrong. I can either change all of these into centimeters, or I can leave them in meters and change 150 centimeters into meters. I think that's less work. So I'm now going to think of one square edge as being the same as 1.5 meters. And that goes back to the first lesson from this chapter, these SI conversions. It's 100 centimeters in a meter, so I just divide 150 by 100. All right, so how can I, draw these things? Well, a ruler is helpful, but for example, if I look at this measurement across the bottom, 24 meters, how many squares is that going to be? Well, I know that every square down here is going to be 1.5 meter. So I need to think about how many times does 1.5 go into 24? How many squares is equivalent to 24 meters, knowing that each square is 1.5 meter? So I need to think really here, what is 24 divided by 1.5? That will tell me how many times 1.5 goes into 24. Again, because every square is 1.5 meters. And so 24 divided by 1.5, feel free to use a calculator, and you get exactly 16. So that means 16 square edges, or the length of 16 squares on this grid here, is going to be equivalent to 24 meters. So I'm just going to go roughly at the bottom and just count 16 squares. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so that's that side there that I'll highlight in yellow corresponds with the 24 meters up there. All right, so once I have that idea, I can do it with all the rest. So for example, if I look at the side E, which I now know is 6 meters. Well, how many square edges is that? Well, each square is 1.5 meters, so I need to think how many times does 1.5 go into 6? And if you're not sure what that is, I can just go 6 divided by 1.5, which is exactly 4. And so the sides of this diagram are both going to be exactly 4 squares high, whether it's this side or this side. All right, so I'm actually almost done. Next I have these sides I've highlighted in green, whether it's D or this other side, they're both 9 meters. So it's 9 meters in real life, or the actual object is 9 meters, but how many square edges is that? Each square edge is 1.5. How many times does 1.5 go into 9? If you're not sure, go 9 divided by 1.5, and you get exactly 6. So again, I'm trying to create a copy of this, so I should count in 6 squares from each side. Oh, I miscounted right here. There we go. And so all that's left now is the top part of this. And all these sides right here are 6 meters. But again, I need to know how many square lengths, because I'm making a scale diagram of this. And so I need to think how many times does 1.5 go into 6, which again, I've already figured out is 4. So fairly easy to draw. 4 squares, 4 squares, 4 squares. There we go. So what I have there is a scale diagram of what I sketched out right here, with a scale of 1 square to 150 centimeters, or 1 square to 1.5 meters. And no matter where I drew this on the grid, my image should be, if it's correct, identical to this for this particular scale. So all that's left now is this part here where we're asked to write the scale in ratio form. So I have the scale written in several different ways, but if I want it in ratio form, that means I don't want any units. And so I'm just going to erase this right here and focus on this last ratio I have written here. 1 square edge to 1.5 meters, or 1 square edge to 150 centimeters. If I want to write this in ratio form, that means no units, I need to first measure 1 square edge. How long, on the piece of paper, how long is this distance from here to here? I will say that's a fairly small measurement, so while I can measure it okay, what I would recommend is I personally would measure all the way across here, which is 26 squares. And I'd measure that whole distance, and then use that to figure out my best idea of what 1 square is. So for example, I measure all the way across, I get about 10.6 centimeters. So I know 26 squares is about 10.6 centimeters. Therefore, 1 square should be the same as about 10.6 divided by 26. And I get something quite close to 0.4, 0.41. I'll say it's approximately 0.4 centimeters. And again, I could definitely just try to measure 1 square directly, but because it is quite small, it's hard to measure with much accuracy. It's going to be more accurate if I measure all the way across and then just divide by 26. So each of those square edges is about 0.4 centimeters. So I'm going to write 0.4 centimeters is the same as 150 centimeters. Well, now I have the same units, so now I don't really need to have the centimeters anymore. I can just say this is a scale of 0.4 to 150. That said, it'd be much nicer if that wasn't 0.4, if that was just 1. So the last thing I want to do is, just to make this ratio cleaner, I want to change that 0.4 to 1. So how do I go from 0.4 to 1? Once I know that, I do proportionally the same thing to this side. Now, 0.4 times what equals 1? Well, I don't blame you if you're not sure. It's actually not a bad number, but I can't expect someone to know just right away. 0.4 times what equals 1? Once I know what I have to do to 0.4 to get to 1, I do the same thing to 150. So 0.4 times what equals 1? Well, I can use division to figure this out. Just like if I asked you 4 times what equals 12. If you weren't sure what that was, you could just go 12 divided by 4, and it would tell you 3, the missing number. Well, right here, if you're not sure how to go, what 0.4 times what equals 1, fair enough. Just go 1 divided by 0.4. Right? Essentially, anytime you're trying to figure out a multiplication statement like this, where you know what it equals, but you don't know one of the factors, that's essentially a division statement. And so I can just go 1 divided by 0.4, and I get 2.5. So that tells me that 0.4 times 2.5 equals 1. So now I can make this ratio much nicer. If I just multiply this by 2.5 and do the same thing here. And so I get to a ratio of 1 to about 375. And there's my ratio without units in a much cleaner numbers than just 0.4 to 150. And again, another way of looking at this is this tells me that this scale diagram here is 375 times smaller in any direction than the actual image, which was being represented up here, of the actual 24-meter wide image. All right.